Hi, my name is Katie Rolls. I'm a Master of Research student working with Hawkesbury Institute for the Environment, and here I will be presenting some of my work analysing the effectiveness of X-ray factotron and simulated fire treatment as techniques for observing adaptive variation in legume seed along an altitudinal gradient. The threat of climate change is well known within scientific research. It predicts the onset of more extreme weather events across the globe. In Australia, it is expected that hot extremes will be more frequent and intense, with higher incidence of drought and heat waves, and less rainfall in southern Australia. Days above 40 degrees Celsius are expected to increase drastically over the next century, with changes occurring at such a rate that species will not have time to adapt. Variation in responses to these changing conditions will set apart species that may adapt and persist from those that may become extinct. Mountain ecosystems may be particularly vulnerable to higher temperatures as conditions become drier and fire risk increases. Soil-stored seed banks will be particularly vulnerable to warming conditions and are ideal for studying response to climate change threats. They are common in fire-prone landscapes, providing large pools of seed for post-fire establishment. The long-term persistence of populations relies on residual seed bank in the soil, and as such they have adapted to fire seasons that exceed their juvenile period in order to reach maturity and replenish seed banks between fires. Their physical dormancy mechanism is broken by high temperatures, typically produced by fires, which break the seed coat, allowing water entry for subsequent germination. A field study by Mark Uy and a team of researchers in 2012 looked into how legume species sourced from populations at different altitudes will cope under projected heatwave conditions. They found that every 1 degree Celsius increase in air temperature equated to a 1.5 degree Celsius increase in soil temperature. This heating under climate change scenarios will have negative implications for soil-stored seeds, causing soil temperatures to heat seeds to temperatures high enough to break dormancy in inter-fire periods, not giving plants enough time to mature and replenish seed banks before the next fire, reducing population size and increasing the likelihood of extinction events. Previous studies have used different methods to assess how plant populations will cope under projected warmer conditions. Altitudinal gradients, where temperature declines with altitude, provide a surrogate for time in climate change studies, as the temperature decline is expected to shift up the mountain gradient as climate warms. Germination experiments conducted by Uy and his team, where seed was subjected to heat wave conditions for 14 and 30 days, showed variation in response based on altitudinal distributions, with tableland populations having lower levels of dormancy. Wharton and Wardle similarly investigated spatial variation in Acacia suaveolens, finding significant variation in size and fecundity. Auld and O'Connell used laboratory heat treatments to simulate the passage of fire. Seeds were heated in soil wrapped in foil for durations of 1 to 120 minutes, at temperatures ranging from 40 to 120 degrees Celsius. They found that temperature was a significant factor in dormancy loss. These experiments reflect the high variability of germination response between species and sites that may be indicators of local adaptation. To build on these studies, we selected species based on their distribution along the altitudinal gradient in the Blue Mountains where temperature decreases with altitude, choosing acacia species for congeneric comparisons. In order to pull apart distributional variation, we selected species that were restricted to warmer coastal areas at lower altitudes, high tableland areas that are cooler, and species widespread across the gradient. Sites were limited to sandstone soils, with replicate sites for each species at a particular distribution and bioregion. Ultimately, 13 species were chosen, with 40 total seed lots. The aim was to estimate seed dormancy and fire-induced germination among bioregions for restricted and widespread legume species, as well as developing non-destructive techniques to predict the response of seeds to climate change. We predicted that seeds in the tableland bioregion will have reduced seed dormancy and thinner seed coats, where restricted species will show greater differences among the bioregions. In order to observe seed response to temperature, each seed lot was subjected to a 10-minute heat treatment, simulating fire, in ovens set at temperatures of 60, 70, 80, 90, and 100 degrees Celsius. Each seed lot had 5 replicates of 20 seed. They were placed in individual glass beakers, labeled with the seed lot ID and replicate number. 1 replicate from each seed lot was heated each time to avoid pseudo-replication. A tray was used to ensure quick placement, minimizing time the door was open and reducing heat loss. Temperature was monitored throughout each treatment. An additional controller without pre-treatment was prepared to obtain dormancy levels for comparison with the same replication. A scarified control where the seed coat was clipped at the aryl end to allow water entry was used to determine the viability of the seedlots. Following heat treatment, seeds were placed on 9 cm Petri dishes containing 1% agar and incubated along with the control at 20 degrees Celsius constant temperature, 16 hours light, 8 hours dark, and germinations were followed for 4 weeks, determined by the emergence of a radical around 2 mm from the seed coat. Cut tests then determined viability. Non-viable seeds were then excluded from the results. X-ray imaging was explored as a non-destructive technique to measure seed coat thickness. Its fast-paced with high replication in each image gives it an advantage over destructive methods such as stereomicroscopy that requires hand sectioning and more precise placement. X-ray also has the added benefit of identifying viability through parasitism and unfilled seeds. Imaging of the seed coat was carried out using an MX20 Faxitron radiography system. It comes with 6 shelf settings ranging from 1 times magnification on the bottom shelf with a beam coverage of 41.6 cm to 5 times magnification on the top shelf having a beam coverage of 8.3 cm. Laser locator cross beams allow standardized positioning in the center of the field of view. A 1 cm scale bar was placed just above the cross-section to be visible in each image for later analysis. Due to the small nature of acacia seeds, images were taken at the highest 5 times magnification, with a plastic grid used to keep seeds in the same position. 10 replicate seeds were used for imaging, set at 26 kV, using the automatic calibration which adjusts the exposure time for optimum visualization. Images were saved as TIFF files and imported into ImageJ, where seed coat measurements were made after setting the scale in accordance to the 1 cm scale bar, and drawing a line from the outside edge to the inside edge. All measurements were taken on the long side of the seed for standardization. So here we see some of the comparisons of the X-ray Faxitron images. The images on the left show comparison between Acacia linifolia on the left-hand side compared to the smaller species Acacia ulicifolia on the right. The coat of the larger linifolia seeds were more easily visualized due to the different densities, while the smaller ulicifolia seeds were more difficult to distinguish the seed coat edges. Imaging the seed at 5 times magnification provided optimum visualization, however it limited the possible replication. Keeping replication for all species and seedlots on the same shelf is important to minimize variance in results caused by different positioning. Lower shelves allow seeds to be dispersed wider and potentially will be viewed at different angles, altering the measurements. On the right you see a comparison between the highest shelf at 5 times magnification in the top 2 images, compared to 4 times magnification on the second shelf in the bottom 2 images. The left 2 images compare settings at 26 kV and 1.2 second exposure time to X-rays to automatic settings on the right, which lengthened the duration to around 5 seconds. This was found to provide better visualization for the measurements. So here we have a graph showing the germination results. The proportion of seed germinated can be seen on the y-axis and the altitudinal distributions on the x-axis. This is broken up into coastal bioregion on the left and tableland bioregion on the right, and there are restricted and widespread distributions broken up within that. So from the experiment we found that the proportion of non-dormant seed was significant between bioregions, with tableland species having higher levels of non-dormant seed. So this was consistent with Mark Ui's findings in 2012. We also found a trend evident for higher germination in the restricted species. Here we have a similar graph showing the significance of the seed coat thickness, with the seed coat thickness shown on the y-axis and the altitudinal distribution broken up in the same way on the x-axis. So the seed coat thickness also showed a significant difference between the bioregions, and it also showed a significant interaction between distribution and bioregion, with restricted tableland species having thinner seed coats. So these are some graphs made using our statistical analysis, comparing the significance of elevation with dormancy on the left, germination in the middle, and coat thickness on the right. We see in the left graph that elevation was significantly related to the level of non-dormant seeds in the control treatment. Seedlots from higher populations had higher levels of non-dormant seeds. In the right-hand graph, elevation approached significance with seed coat thickness, with higher elevations having thinner seeds. This can be related back to the germination results, with higher levels of germination and non-dormant seeds at higher elevations. The results of these experiments, along with the consistency of their findings with experiments by Mark Uy, support X-ray as a method for predicting germination in legumes. It suggests that species with thicker seed coats at lower altitudes will be better able to maintain dormancy compared to thinner seed coats and higher altitudes. Restricted species may also be more vulnerable, with restricted high tableland species being most vulnerable to warmer conditions expected with climate change. Results of the germination experiments have shown some indication of local adaptation, with variation in species response with regards to their distribution along an altitudinal gradient due to variation in the local climates. To build on this research, it would be ideal to perform a reciprocal transplant along the Blue Mountains gradient, taking advantage of the altitudinal and temperature decline. Seed populations will be sourced from high and low elevations. High elevation sites will have replicate seedlots transplanted back into high altitude sites, as well as low altitude sites. And likewise, seedlots sourced from low altitude sites will be transplanted back into low sites as well as high sites to determine how they cope when conditions change. This will involve different stages of development to capture different components. Direct seeding of intact seeds will determine dormancy levels of seedlots, with expectations that high sites transplanted to low sites will have reduced dormancy, and low transplanted to high will have increased dormancy levels as they have adapted to warmer conditions. Results of the direct seeding determining dormancy may be attributed to the seed coat components. Scarified seed planting will determine establishment and survival, which may be influenced by extreme events such as heat waves. The assumption is that local is best and will be better adapted, with seeds planted into foreign environments from where they are sourced having reduced survival. Transplanted seedlings will determine longer-term growth and performance, relating more to mean shifts in temperature. Again, it is expected that local is best, with better performance in species planted into environments matching their home temperature, with warmer coastal environments having best performance. This will include species propagated from the germination studies to see how variation follows through to the growth stages. 4 species were chosen for their abundance along the gradient as well as the distribution range and bioregion. Acacia linifolia restricted to lower altitudes, Acacia obtusifolia to higher altitudes, and Acacia suaveolens and ulicifolia widespread across the gradient. Pulling apart the variation between sites and species will further aid in identifying local adaptation in legumes along the altitudinal gradient and how they will cope through climate change. I'd like to thank my supervisor, Dr. Paul Reimer, for his advice and guidance, Desi Quintens for aiding in field collections, Lotte von Richer and Peter Cuneo from the Botanic Gardens for providing seeds and X-ray facilities.